I hope I'm audible. So today we are going to practice assignment questions from week 8 assignments for environmental geomechanics course. Okay, so let's start. So the first question is about that which of these statements are correct. So if you if you see, all these statements are about pressure membrane extractor, right? And hello. Okay. Now is it okay? Okay. So the question first is about which of the statement is incorrect. So all of these statements are about pressure membrane extractor, right? Now when sir talk about pore solution, where what we do is we take different type of soil, saturated, unsaturated, and partially saturated soil. And what we check the amount of water, amount of pore solution in different type of soil. In to check the pore solution, we use different methods. So the two major instrument or the methods that sir has discussed is lysimeter and PME, which is pressure membrane extractor. So what PME has, as I discussed in last class also, that you take there is a apparatus, and on that there is a plate. You have the you okay. So you keep this cellulose membrane filter on this apparatus, on this plate, and there is a round ring around it. And what you do is you put the saturated or unsaturated soil into these apparatus, and now you apply pressure from the outside, right? And with the help of this pressure, the pore solution from these soil will come out and will collect in the, here there is a container. Sorry. So we have a collection container, and what happen is that when you apply pressure in this apparatus, if there is a saturated soil or a partially saturated soil, the pore solution will come out of it, pass through the cellulose membrane on which the soil is kept, and comes and got deposited to the container from which you measure the pore solution. So it means that PME is used for what? Pore solution. So where it is written in the second, that it is used for collection of pore solution. Now why first and third are wrong? So we'll check that too. So answer is 2, that it is used for collection of pore solution. Now the first point says that it is used to measure pH. No. For pH they have a different instrument, which is a pH probe, and which measure the pH of soil or solution. So what you can do is you collect this pore solution and then further do the pH. But this PME is not used for the pH. Okay. Now that is why first is not the answer. Now what about third? So third says that it works on the principle of Boyle's law. Now what Boyle's law say? Boyle's law state that P1 V1 is equals to P2 V2. It means that pressure is inversely proportional to the volume. But this law actually applied to gaseous phase. So, and PME does not work on the Boyle's law, right? So this is also not a correct answer. Okay, so PME is used for pore solution collection. Now second question again. Hello. Yeah. Okay. Sorry. Yeah. Okay. So it says which statement are incorrect. So second statement is correct. Okay. and incorrect are third and first, sorry. Okay, so second is a correct statement, first and third are incorrect statement. Okay, now second question is, which of the following device are used for pore solution sampling? I explained earlier that two devices are discussed. One is lysimeter. In lysimeter there is a tension and zero tension lysimeter. It means that a lysimeter in which suction is required or not required, and then there is pressure membrane extractor or PME. So apart from these two, no other pore solution sampler or sampling devices are discussed. So answer is both A and B. Okay. Uh, right. Now the third is about which is the indirect technique of chemical characterization of geomaterial. Now when sir discussed the chemical characterization, he said that there are two methods of chemical characterization. So first are direct methods. It means, uh, and then another is indirect methods. Okay, in direct method, what you do is you take the solution out of the system and then you do the chemical analysis using different instrument. So in the direct method, sir has discussed instruments like ICP, AAS, GC, FTIR, like this. Okay, and these instrument we also like discuss in the last lecture also, that in direct what you have, you directly take the pore solution out of the system and you check this pore solution for the chemicals in the geomaterial. So you take the pore solution, you run it through ICP, through AAS, through GC, through FTIR, and comment on the composition, that is what are the metals that are present, if there is any organic matter that is present, all of that you use the spectrometry instrument to discuss. Now in what happen in indirect, they are generally field method. So in this method, in the indirect characterization, what you do is you don't take anything out of the system. You have a saturated soil or an unsaturated soil, whatever type of geomaterial you have, saturated, partially, or unsaturated, it doesn't matter. Whatever you have, you directly put the instrument into that system and check the reading. So for indirect, what he says that there are few instruments. One is impedance spectrometry. Okay, yeah, impedance spectroscopy. So impedance spectroscopy is actually based on the electric current, that you pass the electric current through the soil and you check the change in potential and comment on the chemical characteristics. Okay, so potential, it depends on the change in potential or voltage. Another method, that so this is one, that impedance spectroscopy. The second thing that he says in the indirect is the TDR and FDR probes. Okay, so TDR is time domain and FDR is frequency domain, reflectometer. So what happen is that in TDR and FDR, these based on the magnetic field property. Okay, or what you what happen is that uh, there is a certain amount of uh, so at different time interval, let's say T1 to T2. Okay, and the voltage is provided to the system. Okay, and once it hit a certain type of chemical or a certain um, type of metal, it come back with a lag. Okay, so the whole idea is that if there is anything in a system, okay, for example, I want to study a certain type of ions, if I want to study certain type of metal, so when you provide signal to the system or to the geomaterial, and when after reflecting, okay, that thing is coming back, so there is a lag, there is a difference in the time. So what you do is you measure the time difference, and you measure the change in impedance, or change in the voltage that is provided, and you comment on the chemical. So you have different times: a time when you apply the voltage, and the time when the voltage return back, and the value of voltage, the voltage that you apply, uh, and voltage that you get. And based on that, you comment on the indirect characteristics, or indirect characterization. So as I said, that in indirect, what two things are: impedance spectroscopy and TDR and FDIR probes. Okay. So for this we got the answer that for the indirect we have impedance spectroscopy, yes. AAS यानी कि atomic absorption spectroscopy, no, because what this is for direct. So we use it when you have we characterize pore fluid directly. You have time domain, yes. Time domain is for the indirect characterization, and pH probe is basically to measure the corrosive nature. It's not for the chemical characterization. It is that about corrosity, corrosivity of the soil, and this we'll study further. Okay, that how corrosive a soil is, and because it depends on different uh, level of certain ions. Okay, so pH probe is also not the answer. So for the indirect characterization, impedance and time domain are the answer for this question. Okay, now let's move to next question. It's about the soil salinity. Okay, now when sir discuss about the soil salinity, what he says that, okay, so when he discuss soil salinity, he discuss two major elements. One is chloride, okay, Cl, and another is sulfate, SO4 2 minus. So why? Because these two are actually very harmful chemical, or harmful ions, uh, because they hamper the foundation of the soil. So if in a soil there is a high amount of chlorine and high amount of sulfate ion, what happens is that it corrode the foundation of the soil, and then hence reduce the stability of the soil. Now, and they are basically the characteristics for the soil salinity. Why? I will come to this. Why they are determine of the soil salinity is because, let's say, if you look at the seawater. So seawater has ions, seawater has salts. So major salt is of course NaCl. Okay. So what it has? It has Na and Cl. Right. Other salts could be ammonium sulfate. Right. Ammonium sulfate has what? NH4 and SO4. So um, because seawater has these ions, we know that these ions are basically the reason of salinity of seawater. And what are these ions? Chloride and sulfate. So they basically are alkaline in nature. They have high, they are basic or high pH ions, and hence they actually lead to soil salinity. Okay, so answer is chloride and sulfite. Now, uh, why oxide and nitrates cannot be? Because there is no oxide which actually has pH in the range of highly basic, or also oxides are not uh, basically are the what do you say, are the characteristics of the salinity. Okay, and same nitrates are not, because the formation mechanism and the availability where they are found, it's different compared to chloride and sulfate. Okay, so they are the determinant for the soil salinity, and they're also very harmful because they hamper the foundation of the soil. Okay, uh, now next question is about suction. Okay, so when sir discussed about suction, or you can say soil suction, he discussed that soil suction is of two type. Okay, one is matrix, another is osmotic. Okay, so these why there is another type which is biosuction, but he has not discussed that in detail. So he discussed only these two types of suction: matrix or metric, and osmotic suction. Now the difference is this matrix suction depends on the matrix of the soil. And what is matrix? If um, if this is a block of soil and there is a lot of particles, bigger, smaller, and all, matrix is what occupy these empty spaces in the soil to make it compact. That is the matrix, the finer material in a soil which has which compose of different composition, okay, and variable composition. That is matrix. And these are grains. So these are the two main component of soil, grains and matrix. So two types of suction, one depend on the matrix of the soil, that what is the composition of this finer material in a soil, and how this composition affect the suction or the tension in a soil. Another is osmotic, it depends on the salts in a soil, salt बोल लो या फिर contaminants. Okay, so salts and contaminants in a soil, for example, calcium carbonate. Okay, sodium, magnesium sulfate or something like that. So salts that are present or any contaminants that are present in soil actually affect the osmotic suction. Now, osmotic suction comes from osmosis. Okay, so what osmosis is? We know, we have studied this, that osmosis is when if there are two containers, okay, and in these containers there is two things. One is solvent, one is solute. Okay, we have studied this, that solvent is something in which we are dissolving, and solute is something which we dissolve. So let's say if we have a salt water, water is solvent and salt is solute. Okay, now if we have two container in which in one of them, let's say solute is high, in another them solute concentration is low. Okay, the salt is low, here NaCl is high, here NaCl is low. Then according to the principle of osmosis, if you connect these two containers, then the flow would be from this direction to this direction. Why? From high concentration to the low concentration. So until it reach the equilibrium. Okay, so if there are two different media with different concentration of solute or different concentration of salt, then there will be a movement of this salt or this solute from one geomaterial or one media to another until it reach what? Equilibrium. Okay, once it reach equilibrium, there will be no further movement, and that is the principle of osmosis. And this osmotic suction work on the same principle. Okay, now what it says is, now the question says that suction is directly proportional to moisture content. Okay, so sir discuss two different things. One is contaminated soil, con, uh, contaminated, and another is uncontaminated. So if you have two media, or if you have two type of soil, contaminated and uncontaminated, what happen is that for the uncontaminated soil, it means that there is no salt present. Okay, in that case, suction, okay, uh, okay, so okay, first I'll explain this. So suction is directly proportional to the so okay, so total suction, that means the total pressure that is applied to get the pore solution, or get the pore fluid out of the system, is equals to the matrix suction. It means that because only matrix is affecting it, okay, because there is no salt. But if it is a contaminated soil, then the total suction, it means that the total pressure that you need to apply to the system is equals to matrix suction plus osmotic suction, because there is presence of what, salts in a contaminated system. Okay, so based on this, we actually answer question number 6, that if there are two different type of soil, contaminated and uncontaminated, a soil in which there is no salt or no contaminants, in that soil the total suction is equals to or directly proportional to the matrix suction. On the other hand, in a soil where there is contaminants present or salts are present, in that type of soil, total suction or total pressure applied to the system or geomaterial is equals to what, matrix suction and osmotic suction. Okay, so the answer for 6 is matrix suction of an uncontaminated soil is always less than total suction. The answer is no, because it is equal to or directly proportional to the total suction. It is never less. It is always equal to total suction. Okay, so matrix suction equals to total suction, not less than. So the answer is false. Now we come to this suction is directly proportional to moisture content. Uh, I will shift this to next slide, and then I will explain. Just 1 second. Huh? Okay, wait. I don't think ये हो रहा है. Okay, so for this I have to make a plot. I thought I will make it in a new slide, but okay, fine. Okay, so in this, sir also discuss one thing, which is SWCC. Yeah, or you can also call it SWRC. So what is it? It is soil water characteristics curve or soil water retention curve. Okay, so these are um, soil water characteristic curve or retention curve. What it says is it plots the moisture content with the suction. Okay, and this plot is somewhat like this. It means that when W is moisture, that is moisture in a soil, and this symbol is for the suction. Now this curve says that when the moisture is high, which is this, then suction is low. Okay, and when the suction is high, the moisture is low. It means that suction is inversely proportional to moisture content. Okay, why so this curve says that if a system has a very high moisture or high moisture content, then it needs less suction or less tension, and if a system has a low moisture content, it needs high tension or high suction to get the pore fluid, to get the the uh, the minerals out of the system. Okay, so the answer for this question is false. Now we also know that why suction is inversely proportional to moisture, because if in the last class I discussed the lysimeter, right? So in lysimeter there is zero tension and there is tension lysimeter. In the zero tension we have saturated soil, and in tension lysimeter we have unsaturated or partially saturated soil. It means that if a soil is completely saturated with pore fluid, it needs zero tension. If a soil is partially or unsaturated with soil, it needs suction or tension to get the fluid out of the system. So lysimeter is actually based on this curve itself, this SWCC or SWRC curve, that it is suction is inversely proportional to the moisture content. Okay, so the answer is false. Now next question. Next is about the osmotic suction of soil. Okay, now I discussed this in the previous slide itself, that it is because of the contaminants or salts in a geomaterial. Okay, it's not because of moisture, it's not because of minerals. Okay, because minerals are good. Osmotic suction is not because of the good salt, it's because of the bad salts or the contaminants. Okay, now question 8 is about which of the following technique break the bond between geomaterial and contaminants through oxidation. Now what is oxidation? Oxidation is that you provide O2 to a compound, okay, and yourself get reduced. Now we do this reaction in chemistry, but here let's see what are the exam what are the points given. First is phytoremediation. Phytoremediation is when you use plant for the decontamination. Okay, ion exchange is simple, like what we studied, CEC, cation exchange capacity. It is based on same, that if someone has less positive charge, more negative ions, then there is a exchange. Okay, so it depends on the cation exchange capacity of the soil. Next is air purging, in which you include air or you put air to the geomaterial. Last is bioremediation, where you use bacteria for the decontamination. Now, the thing is, all four of them are actually used for the decontamination. That is to remove contaminants from the soil. But the question asks that which of them actually use the process of oxidation. Okay, now the answer for this is air. Why? Because air has oxygen. So a very simple example that sir has discussed is that uh, uh, near the beach, okay, what happened is that because there is lot of ship that transport uh, materials from the coastal area, so the diesel or the petrol that is used in the ship, that actually contaminate the beach sediments. Okay, so in the region where there is when a soil or the beach sand get contaminated with the petrol or with the oil. Oil is basically what? Oil has organic matter, right? So uh, it this oil is act as a contaminant, and it contaminate the soil. So this, when you purge air, purging is nothing but you have a continuous supply of air, to the soil. When you do air purging, right, to this system, what happens is that because of oxidation, this oil will get oxidized and it leave the soil surface. So generally what happens is, if you put oil into a soil, into a sediment or a geomaterial, the oil will get absorbed or adsorbed to the geomaterial, right, on the outer of this geomaterial. Now, when you include air purging or you induce O2 to the system, this O2 oxidize the oil. ठीक है? Okay, and the soil actually got decontaminated. So answer is air purging, where you induce O2 which oxidize and remove the bond or break the bond between the geomaterial and the contaminant. Okay. Next is about the corrosivity. So corrosivity, so which of the following state of the native soil might show high corrosivity? Now the corrosivity of a soil is that how much it impact the metal. Okay, so we know that in the sediment, in the geomaterial, sometimes we find resources also, but this depends on, let's say we have pipes. Okay, so when, so metal pipes or metal rods that we put into the soil for two reasons, right? One is for the water supply or for the sewage, right? We use pipes, and then we use pipes or we use these angles also, metal angles, in the foundation, right? Wherever we make dams or anything in the foundation, we use these metal angles, metal pipes. So the corrosivity of a soil is that if it actually hamper these pipes or these rods or angles, and make them unstable, make the foundation unstable. So it depends on different things. So one is aeration, then permeability, then conductivity. A lot of things actually affect the corrosivity of the soil. So sir has discussed that there are two type of material. Let's say there is clay and there is sand. So both of them actually are have different rate of aeration. Okay, so clay has low aeration, uh, sand has high aeration. Aeration means that if you have larger pore spaces between between uh, a crystal, if you have larger pore spaces, it can take more air compared to clay, which does not have, because of its small size, it is fine, right? So because of its fine nature, there is smaller pore spaces, hence low aeration. Sand leads to high aeration. Okay, so he discussed these two materials based on their aeration and then permeability, because one of them is highly permeable compared to others. So these all things actually determine the corrosivity of a soil. Now the answer is, which of the four is actually the best or the highly corrosive? First is undisturbed soil. The answer is no. If there is no disturbance to a soil, let's say you are looking at a soil uh, at the top mountain of Himalaya, okay, where no one can go, no one can, uh, not even animals can go. Okay, so in that there is no aeration. Okay, there is, we don't know about the permeability, and there are two way. Okay, I forgot. So one is that something is itself aerated or permeable. Another is you are disturbing it. Okay. So if the soil is undisturbed, it means that no artificial or no man-made factor is affecting. So whatever that soil has is its innate quality. We are not disturbing it, we are not causing any further damage to the soil. Okay, so it does not have high corrosivity. Artificial could be also via animals. If animals walk over it, if animals eat grass, they can also lead to aeration. It means making more pore spaces and hence high corrosivity. Another is undisturbed contaminated. Now, if it is undisturbed contaminated soil, in that case also, even though there are contaminants, but those contaminants are not properly mixed. Okay, they are, let's say they are localized. Okay, they are located at at some places throughout that. This is a pipe. Okay, this is let's say water pipe, metal, and then on localized region there is some disturbance or some contaminants which leads to this corrosivity, but it's not present throughout. So the answer is no. Undisturbed also have less corrosivity compared to what we are coming towards. Contaminant, yes, it has high corrosivity, but there is two cases. One is contaminated soil, another is contaminated with high aeration. Now the answer is this has high corrosive rate because if there is high aeration means more pore spaces. With increase in pore spaces, what happens is that these material, okay, the contaminants uh, get uh, place to act, to to undergo different type of reactions. And with this increase in aeration, it's actually directly correlated that if there is more pore spaces or high aeration, first it's contaminated, it has a lot of chemicals. Another is it has high aeration, there is more uh, oxidation in, this is the word I was looking for, that there is aeration means that there is more O2 supply. So there, what will happen, there is a constant process of oxidation reduction. And even though in the previous slide I said that with the help of oxidation you can decontaminate a soil, but if there is excess amount of oxidation or aeration, these contaminants or these salts actually undergo different reactions and hence increase the corrosivity. So contaminated soil with high aeration is actually have the highest corrosivity. Okay, now which of the following is used to identify the corrosive property of water? So in that, if we look at refractive index, no, refractive index is about light, that what is the incident light, refracted light. So it is based on the principle of light. So it is not a determinant of water's corrosive property. Now plasticity index is not about corrosive property, it is about that if you make a thick paste, okay, so if you make roll of this soil, or the you take a soil, you put water and then enough water to make roll of it. And plasticity index is when you start this roll or of the soil start getting cracks, it means that uh, a moisture content, enough moisture content when there is no cracks in the soil, define the plasticity index. So it is of course a determinant of the moisture content of water, not the corrosive property. Okay, so plasticity index is moisture content, is for the moisture content. Now what is left is Reisner index or Ri. So Reisner index is actually a index for the, that is used uh, for the calcium carbonate scaling, okay, to determine the extent of calcium carbonate scaling. So the whole concept is that if, sorry, this is 3. Um, if water has high CaCO3, then what happens is that, and you have a simple example is, let's say you have a dam in a water where there is high CaCO3 content. In that case, this CaCO3 scaling on the uh, on the dam. Okay, so this is a dam, this is its foundation, and here there is water. Now, how much this CaCO3 got deposited on these pillars or these foundation actually determine the corrosive property of water, which we measure with the Reisner index. So the formula of Ri is equals to 2 PHS minus pH. Okay, pH is the acidic or basic level of water, that what is the pH of water determine if it is acidic or if it has a lot of basic salt. So if it has CaCO3, it means it should have what? It should be towards the basic nature, right? Because calcium is a basic salt. Now, pHs is pH of water in equilibrium with CaCO3. It means that we have a standard water. pHs is standard, where we know that the pH of water is equivalent to the CaCO3 pH. Okay, we take this, and then pH is the wherever we are working, the pH of measured water. Based on this, we determine Ri. So the value of Ri, if it is between 5.5 to 6.8, there will be CaCO3 scaling. But scaling is still okay. Okay. If it is less than 5.5, there will be heavy scaling. But the problem is not with the scaling. The problem is not with the deposition of CaCO3. The problem start when this CaCO3 start corroding the foundation, and hence the stabilization of the dam. So if your Ri goes above 6.8 or above 8.5, okay, um, then it means it become corrosive. So as long as the Ri or the Reisner index of the water is less than 6.8, then there will be scaling of CaCO3, but it will not corrode the system, it will not corrode the foundation. As soon as it goes above the 6.8 pH, which is basically the neutral pH, if you know water, so neutral is at 7. Okay, so and 6 point and above 6.8 there is corrosiveness of the CaCO3. So as soon as this Ri index goes beyond 6.8, the water become corrosive. Okay, so this Reisner index is actually is help in identifying the corrosive property of water. Okay, so for today we are over. If you have any questions, you can ask. Okay. Do you want to ask anything? Okay. Okay, then. Uh, so for today, we are over. And then